In this lecture, we're going to look at two other algorithms for clustering, one based on prototypes and one not based on density. And also, we're going to look at some approaches to validating clustering. So I'm going to start to talk a bit about some problems with prototype clustering. Then we're going to look at affinity propagation, which solves one problem with k-means, which is that requirement that we specify the number of clusters. And then we're going to look at density-based clustering, which abandons this search for prototypes that represent each cluster, and so can be applied better with to different types of problems. And then finally, we're going to look a bit at validating the results of clustering. So first, let's recall what we saw in the previous lecture when we used k-means. And remember that k-means determines the membership of each example to a cluster by looking at the closest centroid. And these centroids are prototypes that represent each cluster. So in this figure here, we can see the centroids marked with the crosses. And so each region is assigned to one cluster based on the distance between each point and the centroids. So each point in these regions is assigned to the cluster corresponding to the closest centroid. So these centroids are prototypes for the clusters that represent the different clusters. Now, this is good when we have globular clusters, and if they are similarly dispersed, then k-means can really distinguish the intuitive clusters that we are seeing, because those clouds of points that fall closer to the centroid correspond to that particular cluster. But this only if we get right the number of clusters. If we don't, if we choose a value k that is incorrect, then we cannot get a good match between the structure of the data and our clustering. And in this case, using k-means with k equals to 2, these two clusters are grouped together in the same cluster. There is another cluster here, and note that some points here that intuitively should belong to this part are actually placed on the green cluster because they are closer to the green prototype than to the prototype for the red cluster. So k-means works well with this kind of globular clusters that are well separated if we get the k value right. If not, then things don't work very well. And it's also not good for clusters that are not globular. So here we can see that we have three clusters, three clouds here. We chose k equals to 3. We have the three centroids here. But since the clusters are not globular, they are not symmetrical around, then we have these problems here where we have these points belonging to the blue cluster, these points belonging to the red cluster, and it's the clustering done with k-means in this case does not correspond to what our intuition would tell us the clustering should be. And also there is a problem when we are assigning the membership of each point to the closest centroid. This means that the frontier between clusters is always at the midpoint between the corresponding centroids, the corresponding prototypes. So for example, here we have this cross here representing the centroid for the blue cluster, this one representing the centroid for the red cluster, and the frontier between the two clusters is here on this region, which seems a bit like overlapping this cloud that should be the blue points, but we cannot do it, place it in a different position because it must always fall halfway between the two centroids, since we are assigning the points to the closest centroid. So this is a problem with k-means when we're trying to do clustering of these kinds of distributions, and it's a problem if we are trying to separate these clusters, but note that for other purposes this may actually be useful. So this property of k-means is useful when we are doing things like vector quantization, as we saw before. So a clustering algorithm that would simply tell us that this is just a single cluster would not be useful to do vector quantization on the colors of the pixels, because it would always put everything in the same cluster and we would not be able to separate into different regions. So these properties that we have here in k-means, where we specify the k and the way the assignment is made and the way the centroids are distributed, may not be what we want in some cases. For example, this kind of clustering, if we wanted to separate the three clouds of points, but it may be precisely what we want in other cases, like vector quantization, where those properties of the algorithm are precisely what is useful for these cases. So remember that when we are evaluating clustering algorithms, we must bear in mind what the purpose is, why we are doing the clustering. So basically, k-means and k-medoids have a fixed number of prototypes, which can be useful in applications like vector quantization, but it may not be very useful in other applications when we have to figure out how many clusters we have in our data. So this is one thing that we can solve while still using prototype-based clustering with affinity propagation. The idea here is that we have three matrices at the same time that represent, one of them is fixed, is the similarity matrix, that represents the similarity between the points, which ends up being that kind of measure that we need to decide whether or not the points belong to the same cluster. So this is the similarity matrix, and in the diagonal we would have the similarity of each point to itself. This is not very useful, but we use that as the propensity for being a prototype. So if we have a higher value in the diagonal of the similarity matrix, we have a higher propensity for our points to be prototypes representing clusters, and depending on the structure of the data, we will have always also more clusters. So the number of clusters will be a function of the way the data is distributed, but it will always also be affected by these propensity values. If we have a very low propensity, then the points will have some more reluctance in becoming prototypes for representing clusters, and so we will have fewer clusters. But the exact number of clusters will also depend on how the data is distributed. Then we have two matrices that we're going to update during the iterations of this algorithm, which is the responsibility matrix that represents intuitively it's a set of messages that points are sending to each other to indicate how suitable the recipient of the message is as a prototype for the sender of a message. So we can see responsibility as kind of a vote, points voting on how suitable the other points are to represent them. So they can allocate a number of votes between different candidates for prototypes. So at the cell ik of the responsibility matrix, we have a value that tells us how much k is suitable to represent point I in a cluster. So this would be the way the points are voting for their representatives. And then we have availability, which is looking from the other perspective, from the candidate k, if that point is available to represent point I. So by using these two matrices, the way of intuitively understanding the affinity propagation algorithm is to think of the points sending messages between themselves, both indicating if they want some other point to represent them, and the representative saying if it considers itself available to represent the other points. So the way the algorithm works is we start with these two matrices R and A at 0, and then we're going to do these updates where we have the first matrix, this responsibility, or the vote that point I is sending for point K to be its representative. We will update it in this way. taking the similarity between the points and subtracting this maximum between the availability of the different representatives. So note that we are looking at the maximum of this expression by going through all possible representatives that are not K. So basically I is considering as it votes for K, it's also considering what is happening to all other potential representatives. So basically we consider the similarity between I and K. The more similar they are, the better K is as a representative of I. But then we are going to look at other available candidates, so the availability of other potential representatives for point I, plus the similarity to point I. And we're going to take the maximum of that for all other potential representatives of the cluster that are not this particular K. And the higher this value is, the lower the vote that I will give to K, because we are subtracting that here. So basically, we are computing for each point a vote that is a function of the similarity between that point and each potential representative, but subtracting that from that the value of this sum for the point, the alternative representative that has the highest score in this particular sum. And this sum is the similarity plus the availability of the other representative to be a representative of a cluster. So initially this part is 0, so we are only considering the similarity relative to the other, but as some points become available to be prototypes, then this is also taking into consideration when considering the votes of each point for their prototypes. And then we need to update the availability. So basically, the availability of a point to be a representative is in this case it will be K being available to represent point I, and we're going to look at the maximum of the votes for all the other points for this particular representative, so all the other that is not I, and we're going to add this to the self-responsibility. So basically this is how the point, how strongly the point feels that it represents itself and it can be the representative of a cluster. So this is somewhat similar to what we saw previously. Basically, we are seeing that K is a good representative for I, depending on what other points feel about K and how K feels about itself as a representative. And we are going to alternate updating the matrices in this way through all the iterations, eventually until we converge and we have some points that are elected as responsible as representative of the others. So this, in this case, this self responsibility this will also give us the availability of the point to represent itself, and basically we are taking this availability as the maximum of the votes that this particular point is receiving. So the availability of any point to be a representative of the cluster will be the maximum of the responsibilities that other points are giving to that point K. And this is the evidence that K is a prototype. So the higher we have here, the stronger the evidence that K is going to represent other points. Okay, so now we're going to identify the prototypes by computing for each point the maximum of its availability to represent any other point, and the maximum of the responsibility that it is receiving. So if this particular point corresponds to the point that has this maximum total, So if we change I for a particular k and we conclude that I and k are the same, then this is a prototype. The prototype will then be the point that has itself as its best representative plus its availability to represent itself. If this k prime here and I are different, so if the k that corresponds to the maximum of this is different from I, then this point belongs to a cluster that has this one as the prototype. So this way we can decide if the point is a prototype or if the point belongs to some other prototype. And now we can see here graphically how this changes during the iterations. So in the beginning we have all the points, or almost all the points, considering themselves to be representatives of their own clusters. So the points are all separated into individual clusters with just a few exceptions here after the first iteration, where this point is considers this one to be its representative, there's another here, and these 2 points consider this one to be its representative. But basically everything is separated into different clusters. But as we keep updating the matrices A and R, so these messages are passing to the points as some points are telling other points they are good representatives, and points are saying that they are available to represent these other points. Then we start having fewer clusters as the points vote for their representatives and start merging together. This is not monotonical. It can happen that then we continue the iteration and some clusters separate, but eventually we reach a stable solution, so we don't have more changes, and this would be the result with this particular data set using affinity propagation. This of course depends on the value that we put on the diagonal. The lower the value on the diagonal of the similarity matrix, the fewer clusters we're going to have. But with these particular parameters that I used, the iterations ended here, and we separated this data into these 3 clusters. So by passing these messages back and forth between the points, they reach the conclusion that these 3 points here are the best representatives of clusters, and this one represents well the points here in blue, this one in green, and this in red. Now this is still based on prototypes. So even though k is automatic, the number of clusters comes automatically from the parameters that we put there and the shape of the data. We do not explicitly decide how many clusters we are going to create. It's still clustering based on prototypes, and you can see effects like this when we have this kind of shape in our data. So in this case, the affinity propagation algorithm created 4 clusters, and we can see that this is a fairly strange cluster where you get a part of this first half circle here, and then you get a small part of the next one, and also this division into 2 clusters here and here does not seem very intuitive. So we can let the algorithm try to find the best number of clusters based on the value that we give in the diagonal of the similarity matrix, but it's still based on prototypes, so it's looking at the similarities between the points, in this case given by the distances, and it doesn't matter, doesn't care if there is this empty region here. These points are still close to some prototype that was chosen there. If you want to use affinity propagation with scikit-learn, these are the defaults here, a maximum of 200 iterations. This is a damping factor for the messages and the updates on the matrix to avoid large oscillations. And you can then set an affinity matrix or just set it to Euclidean. If you use Euclidean, the affinity matrix is computed based on the distances. Otherwise, you can actually give a matrix. If you have other measures for the affinity and give yourself the matrix. This is the preference that can be automatically computed by the algorithm. This corresponds to the diagonal of the similarity matrix, or you can specify your own a different value for that. So basically, with this affinity propagation, you can fit and then predict the clusters where each element in your data set will belong. Another approach, a different approach without prototypes, is an example of that is DBSCAN. This is a density-based spatial clustering with noise, and the algorithm considers two parameters here. There is an epsilon value that defines the neighborhood around a point. So this is a neighborhood with radius epsilon, and this neighborhood will contain a set of points when we measure around each point this radius of epsilon. And another parameter is the minimum number of points we require inside this neighborhood in order for a point to be considered a core point. So a point is a core point if it has at least this number of points, this parameter, inside a neighborhood of radius epsilon. And then we have this definition that points are reachable if they are directly reachable, which means that they are in the neighborhood, or if we can go from one point to the other always through reachable points. So by going through neighborhoods of other points. And the idea is that we're going to cluster together points that are reachable to each other. So if there is a path through neighborhoods of points connecting 2 points, these 2 points will belong to the same cluster. To achieve this, the algorithm consists of visiting each point, measuring how many points we have in the neighborhood of radius epsilon around this point P. And now we have two possibilities. If this number of points in the epsilon neighborhood is lower than the minimum number required for a core point, we are going to presume that this point P is noise. That is, we're going to assume that it is in a low density region, and so it does not belong to any cluster. If not, if it's at least as large as the minimum number of points, the number of points around the neighborhood, then we're going to create a cluster with this point P as one core point of that cluster. And now we're going to look at the neighborhood of point P, and we're going to add to the cluster all the points. So if this is a core point, if P is a core point, we're going to add to the cluster defined by this point P all the points in the neighborhood of P. Now, it may happen that when we are adding points in the neighborhood of P to the cluster, this point Q may itself be another core point. And if that happens, if we add a core point to a cluster of another core point, then what we do is we merge together the two clusters. And they become the same cluster because we know that they are connected to each other by the neighborhoods. The result of this is something like this. All these points here in black were considered to be noise because they don't have enough neighbors around them, and they were never put in a cluster of some other core point because they are too far away from the high density regions. Then we have this blue region here, where we find many core points because it's a high density region, and since there are core points that are neighbors to each other, the several clusters that the algorithm is finding will end up being merged together in a single cluster. And the same thing happens here in the green cluster. All the core points are put into the same cluster because there are paths between them following just the neighbors. So this is an algorithm that can handle these different shapes. It can handle noise, so it has the possibility of not assigning a point to any of the clusters, and the point is left outside. and it's not based on prototypes. Note that these core points are not prototypes that represent the cluster, because one cluster can have many core points. All of these represented in circles with a white interior are core points, because they all have a large number of neighbors in the epsilon neighborhood. These ones that are full were initially considered to be noise, potentially noise, but ended up being put in one of the cluster because they are in the neighborhood of some core point. And so they also belong to the cluster, even though they are not core points. The ones that are in black are not core points because they are in low density regions, and they are also too far away from core points to belong to any cluster, so they are left here outside as noise. But note that even though this set of core points is giving the shape and defining the cluster, there is no individual core point that is a prototype for the cluster. So this avoids that this kind of problem that we had, for example, with k-means or affinity propagation, where we can have these strange clusters with some discontinuities. Here, with DBSCAN, this doesn't happen. The discontinuities are taken into account because there is no path between points here and points here going through the epsilon neighborhood of a set of points. So these clusters become disjoint, and everything in these in each of these clusters is joined together because there are paths going through the core points and the neighborhoods in this case. So DBSCAN, you can use the DBSCAN class in scikit-learn. Eps is the epsilon value for the size of the neighborhood. Mean samples is the minimum number of points that we have that we need in order for a point to be a core point. And this is the metric. It's by default it's Euclidean, so it uses the Euclidean distance, but it can be a pre-computed matrix with the distances if you want, or it can be a callable object, a function that gives you the distance between the points. So this is what is used to check if the points are inside the epsilon neighborhood. Okay, so we saw now three examples of clustering algorithms. We saw k-means, where we specify the number of clusters, and it's a prototype-based clustering. So each point is assigned to the cluster that has the closest prototype. We saw affinity propagation, that is also prototype-based, but it's a different algorithm where the points are voting for their representatives, and so the number of clusters will also depend on how the data is distributed. And we saw DBSCAN, where the clustering is done based on the density around each point, and then points that are neighbors will be merged together in the same clusters. So we have different ways of clustering the points, and if this was supervised learning, we could try to evaluate everything just by measuring the error when predicting some value that we would observe in the data, some target value. For unsupervised learning, we do not have this straightforward measure, and we need to assess how good the clusters are depending on what we want to do. So there are different contexts that we can consider here. We are trying to figure out if the data has some structure, and then so basically we can be testing whether or not there is some kind of structure in the data. So we need to consider the results of clustering given that objective, or we want to determine the ideal number of clusters to group the data according to some criteria, how well some computed clusters fit the structure of the data, or maybe they fit some information that we have for outside the actual features. So maybe we have some class labels or something like that, and we may want to compare our clustering with those external indexes. We're going to see this a bit better outside in the next week in the context of the second assignment. So looking at information outside the features that we are using for clustering, and this is analogous also to comparing sets of clusters. But today we're going to look at this kind of evaluation of clustering and some ways of doing this by looking only at the features that we're using for clustering. So unsupervised clustering validation, for this we can measure different aspects of the clustering. The cohesion and separation of the clusters, some measures, for example, quadratic error in the distances between the points that we have in the clusters, or we're going to see a silhouette score which compares the average distance inside each cluster to the average distance between points from one cluster and a nearby cluster. So these indexes can give us some idea of how good our clusters are, but only in the perspective of trying to optimize the separation between the clusters and the cohesion of each individual cluster. So the cohesion measure would be the sum of the similarity of each pair of points, considering all the points that belong to this particular cluster. So the cohesion of cluster I is the sum of the similarity of all pairs of points belonging to cluster I. The separation between the clusters would be this measure, but between points of one cluster and the points in the other. Note that this similarity measure can also be a dissimilarity measure or a distance, and in that case we need to adapt these measures here. But the general idea is that we can look at the cohesion of each cluster by looking at the pairs of examples inside the cluster, and then compare different clusters by looking at pairs of examples between one cluster and the other. So in this case, they are both X and Y in cluster I, and in this case, X belongs to cluster I and Y to cluster J, and we are looking at the pairs between different clusters. If we are using prototype-based clusters, we can compute this more simply by looking at all the points in one cluster and comparing it to the prototype. So we are measuring a similarity or a dissimilarity or a distance between each point and the prototype of the cluster. And the separation between clusters can be estimated or measured simply by the similarity of the prototypes. So we know that the prototypes are representing the clusters. The more farther apart or dissimilar the prototypes are, the greater the separation. The closer together, then the smaller the separation between the clusters. We can also, if we are using distance, we can use the squared distance, for example, between points and the prototype, and we have this sum of squared errors that we can do to summing for all the clusters that we have the distance between all the points and the prototype of each cluster. Remember, we saw this as the loss function that we're trying to minimize in the case of k-means, where basically we want to group the points in a way that the points are always as close together, as close to their representative, to the centroid for their cluster as possible. Another score that we can use is this Situate Score, which considers these two measured quantities. A is the average distance between from one point to all points in the same cluster, and B, or BI in this case, the average distance of that point to all points in the nearest cluster. So we can compute the Situate Score for one particular point by looking at the difference between the distance to the points in the nearest cluster minus the average distance to the points in the same cluster. And then we divide that by the maximum of the two. So basically, if the distance to points in the other cluster, in the nearest cluster, is larger than the distance to points in the same cluster, this will be positive, and so we'll have a Situate Score greater than 0. And if this value here is much larger than this one, or the distance to the other cluster is much larger than the distance in the same cluster, then this silhouette score will go close to 1. This would be the maximum possible value. On the other hand, if the distance to points in the same cluster is larger than the distance to points in the nearest cluster, this expression here will be negative, and so we will have a negative silhouette score. Basically, if we have very tight clusters that are well separated, the silhouette score will tend to be high, and we can compute. This is the expression of the silhouette score for one particular point, but we can average this value for all the points in the cluster and then for all the points in our data set. So this is what you get when you measure the silhouette score, is the average for all points in the data set. And this will be a high value if we have very tight clusters that are separated, and it will be a negative value if the clusters are mixed with one another. So let's see some examples here. In this case, we have these three clusters, red, green, and blue, and this has a silhouette score of 0.733 because the clusters are relatively tight, and the distances between points in the same cluster tend to be much smaller than the distances to the nearest cluster. If we get the number of clusters incorrectly, then in this case the silhouette score goes down, because now we have these clusters that have large distances here, and now we also have these small distances between different clusters. So there are some points here which are pulling down the average of the silhouette score. And this also doesn't work well if we don't have globular clusters. For example, in this case, we also have a low silhouette score because these clusters are not very good. But even if we have intuitively good clusters, such as in this case, the silhouette score can be low. Note that when we measure the distances inside this cluster, we have very large distances here that are actually larger than distances between the blue and green cluster. So the silhouette score in this case is rather low, even though the clusters are pretty good, at least intuitively, because they make sense the points to be clustered in this way. So the silhouette score is better for compact clusters like this, and also it can have problems when for example, here in k-means, when you have frontiers like this in this kind of clusters. So we have a very small distance between points in this cluster and points in this cluster, and this also brings down the silhouette score. So the silhouette score is practical for an assessment of how good the clusters are, in the sense of being tight and well separated and globular. Note that in some situations the silhouette score does not make much sense because the clusters are not globular, and so even if they are good, you can have a low silhouette score. So basically we have been looking here at internal indexes, which are these kind of indexes: cohesion, separation, silhouette score, and so on. There are external indexes or relative indexes when we compare, for example, clusters with class labels if we have our data labeled, or we can compare different clusterings created by different algorithms, for example. We are going to see some examples of this next week, but the main point that I wanted to stress here is this point that validating clustering is not a straightforward process like we saw with classification or regression, where we can have some error measure and then just measure the error and decide which model is best and which one is working better for our data and so on. With clustering, the problem is that we have many different ways of measuring some attributes of the clusters, but especially we have different objectives and different purposes for clustering and different kinds of distributions of data, and so we must align our metrics when evaluating the clustering, both to the structure of the data and to the purpose of clustering. Why do we want to cluster. For example, using Situate Score to evaluate vector quantization would make no sense, because what we are trying to do to separate these continuous values in representatives would not possibly have anything to do with the Situate Score. So remember that for clustering, you cannot simply use these indexes. You need to think about what the purpose of clustering is and what will make sense when evaluating the results. So to sum up, we saw two types of prototype-based algorithms for clustering. K-means, which we covered in the previous lecture, and in this one you specify the number of clusters, which is good in some applications like vector quantization, but may not be very practical in other cases where we don't know from the beginning how many clusters we should have. Then we saw affinity propagation, which is another prototype-based clustering method, but one in which the number of clusters can be influenced by the parameter that we give, the diagonal of the similarity matrix, but it also depends on the structure of the data, and the clusters will emerge as a function of how the examples are distributed. And then we saw a different approach to clustering, which is not based on prototypes, but in this case, DBSCAN, it's based on density. Clusters are defined as sets of points that are close together in a high density cloud and separated from other clusters by low density regions. And then we saw some ideas of how to do cluster validation in the context of unsupervised learning, where we don't have labels to compare to, and we have these metrics for cohesion, separation, Situate Score, to assess how tight and how compact the clusters are and how separate they are from each other. But note that this may not be a good indicator of whether or not the clustering is what we wanted, because it depends on what we want for clustering. Next week, we're going to see this type of cluster validation a bit better in the context of the second assignment, where we can actually compare the clusters to some labels that we may have, or clustering it with one algorithm to clustering with another, and so on. So this is, if you want to read more on affinity propagation, this is the original paper, and this is the original paper for DBSCAN. So if you want to read these papers, you'll have more details on these two algorithms. And also you can consult the scikit-learn documentation on clustering. There are lots of examples to illustrate how you can use these algorithms.